body fixed axis forces. And we've gone ahead and taken this cross product and substituted in, so we got the three equations for U, V, and W. So the equations and three unknowns. What we need now is this thing. And it's composed for an airplane of a gravity vector in the body fixed axis. So we need to figure that out. And then the aerodynamic forces, like the lift, drag, pitching moment, lift, drag, and side force. So the first thing we'll work on, I'm trying to write a G and a Q at the same time. The first thing we're going to work on is the gravity vector, and we need it in the body fixed axis because this equation is in the body fixed axis system. So we know the gravity vector in the Earth fixed system, it's in the Z direction down. So we have to transform it from Earth to body using the Euler angle transformation. And this is easy because GE, not General Electric, but the gravity vector only has a Z component. So that transformation matrix, we don't even need to write the other components for it. Because we've got all that other stuff in these positions that are just going to get multiplied by 0. And all we need is this last column. And it makes sense that it depends upon theta and phi, because if the airplane is pitched up, then the gravity vector is going to change with respect to theta, that pitch angle. In fact, if we're pointed straight up, then the gravity vector is going to be in the negative x direction. Likewise, if we bank the airplane completely sideways, then the gravity vector is going to be in the positive y direction. So it's going to depend upon phi as well. But this multiplication is easy. We get and that's what we stick in for this. And then the aero forces, we still need to figure out, but we're going to write some names for those. We're going to call the aerodynamic force in the x direction, capital X, the aerodynamic force in the y direction, capital Y, and the one in the z direction, capital Z. And then in a bit, not today, but another day, we'll figure out where the lift acts, which direction the lift acts, the drag, and so on. So we're going to substitute this and write the whole set of equations here in a minute, as soon as you guys are caught up. I hear you had a structures test. Did you survive? I guess so. You're still here. Not dead yet. So here's the whole set of equations. We got the force vector aerodynamic. Here's the gravity vector. And then there's the v dot. I forgot a dot on here, didn't I? And then here's the cross product thing. So that's those cross products that we did, that's omega cross V. And these are the force equations. So if I said, which is the X force equation, which one would you point to? The top one. Why? Because you see an X, right? So this is the forward X direction. This is the Y force equation, so that's sideways. This is the up and down Z force. What if we didn't have that? Now you still know because it's the top one, right? But what else could you look at? The force in the X direction is equal to the mass times the acceleration in that direction, right? So you could look at the X velocity and identify them that way. Because that's just sum of the forces equals mass times the acceleration in that direction. This other stuff, you could actually look at this and see that you don't have any P's in here. And we don't have any U's because this is omega cross V, so you don't get, in the I direction, you get the J and K components that cross into I, right? But that's too hard. You could just look at the dots here and see which one's which. So there's one more thing we need to wrap up before we go into dealing with these equations, is that there are the body fixed axis system, stick that on the airplane however we want. So here's our airplane. Here's the center of gravity. Here's the horizon. Like that. A natural way to stick the body fixed axis system on is to point it out the nose, like that, and then down like that, right? It kind of fits the airplane. That's the way we've talked about it, is X is out the nose, Z is down. That's not very perpendicular. Let me fix that. And then Y is that way. But, I mean, where does it go through the nose of the airplane? We could put it through the very tip of the nose, or maybe we tilt it up a little bit to make sure that it goes straight through the whole airplane, right? It's kind of arbitrary. It really is arbitrary as how we attach it. We do know that this angle is the pitch angle of the airplane, theta. And then if the velocity vector is like this, so that's the direction the CG is going, then we call this angle the flight path angle, gamma. So let's define those. Theta, this is the Euler pitch angle. And then gamma is the flight path angle. Because if you follow the CG, it's going to go in the direction of the velocity. So if you followed a flight path, it's going to go, the CG is going to move along like that. So that's the angle of the velocity vector relative to the horizon. And then what we just figured out was where the gravity vector is in that axis system, right? But let's leave that off because I don't want to clutter this up too much. Now, maybe you're saying, hey, in AE324, what did you call the flight path angle? Do you remember? In my class, we talked through this. If you had a different instructor, maybe they talked through this or not. Do you remember back then what was the flight path angle called? When you were doing the gliding flight or the climbing flight, right, where you were tipped up and climbing or you were gliding and going down. Do you remember the symbol? If you don't, maybe it's good. The what? No. I'm just talking about in chapter 6. Yeah, it's a performance chapter. You go through gliding flight. Did you guys cover? In my class, I know we did. Did you guys cover that? I'm pretty sure you did. Maybe I shouldn't tell you because in AE324 you called theta was the flight path angle. And I don't know why he does that, but he did. But the most standard is gamma is the flight path angle, and theta is the Euler pitch angle. So if you don't remember this, good. But if you ever go back to your 324 book and you go, hey, well, theta there, why is he calling theta the flight path angle? It's just because that's what he did. So in most classes and in this class, gamma is the flight path angle, theta is the Euler angle up to the axis. So far, so good, right? Now which way is lift? Lift is perpendicular to V infinity by definition. We could define it any way we want, but that's what most people do. And then drag is parallel to V infinity, right? Yeah. Yeah, this is the velocity of the airplane. We're not saying that there's any wind or anything. And so the relative wind coming in is just the opposite direction. Yeah. So if we stuck with the XZ axis system that we've defined, pointing out the nose, we have to resolve the lift and drag. Into the X and Z directions. So it'd be lift times cosine of alpha, lift times sine of alpha. That's the forward and downward components, and the same thing with the drag. No big deal. We can just do that. But there's another axis system that is easier to deal with those forces in the body fixed axis system. And so sometimes people use this. It's called the stability axis system. And this is most often used for aircraft dynamics, meaning the equations of motion. You don't have to use it. It's just the standard that's used in this book when we start dealing with these equations of motion. So when we start to fill in what I erased here, the X and the Y and the Z, most often we do this in the stability axis system. And so I need to tell you what that is. And it's still an X, Y, Z axis system. It's not any big deal. We just say, okay, we're not going to point X out the nose. We're going to point X along the wind. So put an S on that for stability axis system. And we can do that. We can stick the axis system with Velcro, if we wanted, on the airplane, right, in any direction we want. So we're going to say, we're flying at 100 knots at an angle of attack of 5 degrees. That's the direction XS is. And then here is the Z axis angle here. And we use that, and that's the stability axis system. So what is the pitch angle, theta, of the stability axis system? Because remember, the Euler angles are just the rotations to get up to that axis system up in the air. Well, it's just the angle there. Again, theta is the pitch angle up to the axis stuck on the airplane. So in the stability axis system, theta, oh, look at this, theta is gamma. So maybe that's why he did that in 324. But he doesn't talk through that too much. It's no big deal. It just means that if we decide to use the stability axis, we stick it on the airplane. Usually the angle of attack is pretty small, right? Like 2 or 3 degrees. So these are actually a lot closer together than what I'm showing here. The nice thing about this, though, is that notice that the z-force along the zs axis is negative the lift. So that's easy. And the x-force, they sound like branches of the military or something, only with superheroes. This is going to be minus d, right? So this makes it easier when we start dealing with the equations of motion. Other than that, everything else is the same. We just still have theta. We still have all of the other motion variables, u, v, and w. It's just they're forward, down, and sideways is like that. So we have over here 3 equations, x, y, and z force equations. And in addition to these, we have 3 moment equations. These are the ones you worked on in the previous homework, where you did all those cross products with the angular momentum. And so we have equations for L, M, and N, and these are a lot more complicated. So rather than writing them on the board right now, I'm going to pull up the page in your book that lists. So the top equations are the 3 that we wrote on the board, right? Exactly the same. The E on there means that their velocity is related to the Earth, which means there's no wind. All right, those are airspeed velocities. And if there's no wind, then the velocity of the airplane matches its velocity relative to the Earth. So we're neglecting wind here. So the top 3 equations are the force equations that we wrote, and then those next 3 are the moment equations. And they're purple just because I had a purple pen, not because I'm pro K-State or anything. I guess the top equations are KU, the bottom ones are K-State. I should have made the kinematic yellow. It doesn't matter. So who's red? St. Louis Cardinals, I know. I grew up over there. Huh? The Chiefs are red. There we go. It's Kansas City Chiefs are the kinematic equation. Those are the equations that relate theta dot, phi dot, and psi dot to P, Q, and R. Remember we talked about those. This is just a transformation. And they're kinematic because they aren't dynamic. It's not mass times acceleration is the force. And then he lists what he calls the transformation from the UVW to X Earth, Y Earth, Z Earth. And we talked through that. If you wanted to follow your flight path on the Earth, you would want to know these. These are the velocities of whether you're flying north, south, east, or west. And so this would allow you to figure out, oh, my airplane took off from Wichita and landed in Denver, following the flight path. And notice that they're all coupled together. Up here in these equations, we need theta and phi. And where do theta and phi come from? They come from these equations down here in terms of P, Q, and R, but where do P, Q, and R come from? They come from these equations here, P dot, R dot, Q dot. So often this set of equations these top 6 equations are called the 6 degree of freedom equations because they govern the dynamics of U, V, and W, and P, Q, and R. So there's 6 variables, 6 equations, 6 unknowns. Sound complicated? Yeah, because now we've gone from our 2 mass system, which was 2 equations and 2 unknowns, to 6 equations and 6 unknowns. Airplanes are not easy. And then we have the kinematic equations. If you look here, we've got sines and cosines, and we've got variables like P times Q. So this would be like x squared or x1 times x2 in the mass equations. And it turns out you cannot Laplace nonlinear equations because the formula doesn't exist. If we wanted to Laplace x squared, you can't do it. It just doesn't work. It's nonlinear, and Laplace and integration is a linear operator. So what do? Give up, go home, call it good for the semester. And then the pilot says, oh, so how does my airplane behave when I do a quick pull-up and there's some dynamics going on, and then I add a bank, and you go, I don't know. Just jump in and see how it does. So we want to analyze the dynamics. We want to see what happens. So there's 2 ways to do it. How are we doing on time? Okay. We can either do a process where we linearize these equations about a cruise condition, and I'll show you that. That will be what we get into next time. So there's a way to neglect small terms if you do linearization. I don't know if you've done that in another class. Sometimes it's done in aerodynamics when you're looking at friction flow and the viscosity, especially high-speed flow. But also, we'll walk through step by step how to do that, and that's on your next homework assignment. The other method is to integrate these numerically on a computer. And that's how X-Plane does it. Although I'll show you the simple version. It actually uses a much more powerful numerical integration scheme. But the way this works is that we use the definition of a derivative. So let's back up from the complicated airplane equations, and let's look at a simple first order differential equation. So it's going to be x dot minus 5x equals f with initial condition of 0. So the force can be a function of time. X and it is, of course, a function of time. And what we do now this is linear, but don't let that, I mean, this method works for linear or nonlinear, is you can integrate this equation by we take x dot and we write it as an approximation over a small time step. Right, so that's approximately x dot. And in math, if you take the limit as delta t goes to 0, you get exactly x dot, and that's the definition of a derivative. And really what you're doing, go all the way back to Calc 1, is you have a curve, and you have 2 points here. One at t and one at t plus delta t. And what we're really doing is just calculating the slope of that, right? The rise, x over the run, well, crap, I wrote that wrong. This is, what was I thinking? All right, so there's the dependent variable there, and this is t, and this is t plus delta t. Okay, so you calculate the rise over the run, that's all that really is. It's the slope. And so this is approximately equal to 5x at t because as long as we put delta t in there and we don't take the limit, it's approximately equal to that. And then what we can do is we can solve for this point at the next time step. Did I lose this? No, I flipped the sign. Okay. So what that says is if I know my values at the current time, I can predict where I will be 1 second later or 1/10 of a second later. And this should not be a surprise because we can do this fundamentally if we know how fast we're going and we know where we are now. In 1 second, we should be able to predict where we are a second later, right? You're just integrating that velocity. So this, we could start at x at time 0, our initial condition, and then we could calculate x at t plus 0.1, and then we could use that value and stuff it back in here and calculate x at t plus 0.2 and just keep marching forward. And that way we could find our position as a function of time all the way forward in time. Now, did you guys talk about this in 227? You talked about numerical integration at all? So you did some of this there, right? So you can do the exact same thing with the dynamics for the airplane. We have single derivatives in the equation. So in the equations of motion, everywhere you see u dot, you write everywhere you see v dot, you do the same thing. Everywhere you see w dot, you do the same thing. P dot, we could do the same thing. Right, all the way q dot, r dot, theta dot, phi dot, psi dot. Every variable that's a derivative, we approximate with its difference. This is called a finite difference. Still got some time, good. So we do that, and then we solve, and so we can predict the new velocities at the new time step based on where it is now and what forces are applied to it. So we do that with the equations of motion that we were looking at on the board. All right, so in this equation, u dot gets replaced by u of t plus delta t minus u of t. Same for v dot, w dot, p dot, r dot, q dot, phi dot, theta dot, psi dot. We end up with 9 equations that at every time step get solved for the new values at the next time step. P, Q, and R. And we also need to send it to forces, right? We've got the aerodynamic forces and so on. Well, what are the forces? What controls this thing? We'd want to send it the aileron, elevator, rudder, and throttle position at the current time. And then inside here, we do all the equations that are then going to tell us the state at the next time step. And that's numerical integration. And that's exactly what X-plane does. Is it uses the equations of motion and a pretty complicated aerodynamic model. And then it takes your elevator, aileron, rudder, and throttle, flaps, and all of the other inputs into the equations. And it says, okay, I'm sitting on the runway still, ready to take off. And then you kick the thrust up and take the brake off. So that creates a net force forward. And it jumps forward 1 time step, and the airplane moves a little step down the runway. And then it calculates psi, theta, and phi, because it has to know where the Earth is relative to you in the cockpit so that it can display the right thing for you to see of the real world scenery. And then it takes one little more step, and you go a little bit further down the runway, and you keep going step by step. You pitch up, you angle, you climb in the sky, and it just keeps integrating forward. Now, if that sounds like there's a lot of error that could build up in this, it can, because if you fly for an hour and a half, there's little tiny errors that build up as you do this, and that's just numerical integration error. And so what he does is a fourth order Runge-Kutta method for two reasons. One, it's fourth order, so it's 4 times, actually it's a lot faster than our first order method that we did. It predicts with an aircraft design, they'll develop the equations of motion, they'll do wind tunnel tests to get the forces and moments right. And all of that, it ends up in a big database that is used to drive a flight simulator that pilots and control engineers can design control systems for to evaluate the airplane before it ever gets off the ground. So that's essentially what you're doing in X-Plane, is you're taking our design and then flying it to see how well it behaves in flight simulation. We're out of time, right? Probably. Well, we're done anyway, so we'll call it for today.